Okay, so today we're going to talk about finding maximums and minimum values of certain functions. And of course, this is kind of going to be a big theme in this entire chapter. So today we're going to start with a bunch of introductory stuff, defining a bunch of things, and then later on in this chapter, we're going to find other ways of maximizing and minimizing certain situations. Okay, so basically, just to kind of quickly summarize what we're going to be doing in this chapter is the following. The goal of this chapter is to work with problems that help optimize specific cases. And when we're saying we want to optimize specific cases, if you think about it, well, then these problems could be solved with the ideas of maximums and minimums of functions. So just to kind of quickly make a comment on this, see, why do we want to maximize or minimize when we're trying to optimize something? So if I have, let's say, a function that describes the profit of my company, what do I want to do to my profit? Obviously, if I own a company, I want to maximize my profit. So we care about finding the maximum of that function that describes my profit. So that's kind of what's going on here. So let's first start off by defining kind of maximums, minimums. And these are things that you probably did see in analysis, but I'm going to go ahead and define it anyway. So let's start off with our definition. We could say that a function f has an absolute maximum, which is also known as a global max. So if you hear the words absolute maximum or global maximum, they mean the same thing. So at C, if f of C is greater than or equal to f of x for all x in the domain of f. So one comment I want to make here is, look, we define or we kind of talk about the location of absolute maximum through its x values. So when I say, look, my function has a global or an absolute maximum at C, what does that mean? If I go to x equals to C on my graph, that the y value at x equals C is going to be the largest amongst all of them. So always remember, when we're describing the location of an absolute maximum or even a minimum, we always define it through their x values, okay? So just keep that in mind. So then what do we say? What's f of C called? Okay, so remember, C is the x value in which we use to locate the absolute maximum. Then what we could say here is that the number f of C is called the maximum value of f. So if I say, what is the maximum value, then I'm asking you to pretty much give me the y value. Okay, so remember, location is always described through the x values. The maximum value of your function is described through the y values. Okay, so now let's also define an absolute minimum. So a function f has an absolute minimum at C And by the way, absolute minimum or global minimum means the same thing. So just like the global max. So just like for the global max, what are we saying? The y value at C is greater than or equal to all the other y values that this function takes on. So for absolute minimum, we're going to say if I have an absolute minimum at C, what does that mean? The y value that my function takes on at C should be less than or equal to all the other y values of the function. So then this is what? Is the absolute minimum at C if the y value at C is less than or equal to all other y values of your function. Okay, so this is for all x in the domain of f. So then we could say that the number f of C in this case is called the minimum value of f. And one other comment I want to make, or one definition we're going to make. So the maximum and minimum values, so the maximum and minimum values of f are called the extreme values of f. So in other words, if I ever ask you to find the extreme values of f, I'm asking you to find the global max and the global min, the y values of the absolute maximum and the absolute minimum of your function. So let me just draw a picture real quick, just that describes the situation here. So if we have a function that looks like this, if I do something like this, and I'm going to label this, I'm going to call this A, B, C, D, and E. So my question to you is, just by looking at this graph, where's my absolute max and absolute min? So when you look at this function, and by the way, this function ends at A and starts at A and ends at E. So what you look at this, what's the largest y value that this function takes on? See, the largest y value that this function takes on is at D, which that y value. So this is my absolute maximum value. Okay, so my absolute max is at D, and then my absolute min, what's the lowest it takes on? This is at A. So this is my absolute minimum value. Okay, so if you look at this, what do I have? My absolute maximum is at D, and my absolute minimum is at A. But my question to you is now, how about, how about B, C, and E? Like, what happens at B, C, and E? What do we call those? I mean, clearly they're not absolute maxes and absolute mins, but what do they call them instead? So this is actually going to get us into the next definition. So let's define this next definition, and then we'll kind of go back to this picture and we'll see what actually, how we could identify this. Okay, so what we could say is that a function f has a local maximum at C if f of C is greater than or equal to f of x when x is near C. Okay, so what is this basically saying? What is this saying? And another way of looking at it is, another way of saying this, which is equivalent and is more commonly said, is what are we saying? F of C is greater than or equal to f of x for all x in some open interval. This is basically saying the same thing. So what's a local maximum? A local maximum means, could you find a value? Like if I come back to this picture, see that now let's turn our attention to x equals b. Over here, if I find a small open interval, see, what am I looking at? When we say a local max or something that's local, I want to stay close to b. So if I pick an open interval that includes b, what do I notice? In this open interval, and when we say an open interval, we want that open interval to be a small interval. In this open interval, what's the largest, or where is my largest y value located at? Which is at b. So that's what a local maximum is. And in fact, if you look at it, it's a local maximum because it kind of goes up and then it hits a maximum and it comes down. So what's the difference between a local maximum and a global maximum? Global maximum considers the y value amongst the entire graph, okay? So this clearly is not the largest y value that this graph takes on. But local maximum means if you stay local, if you don't go too far away from b, does this act as my largest y value? And if the answer is yes, then that's a local maximum, okay? So in this picture, what do I notice? I have a local maximum at b, and how about d? What do you think? Is d also a local maximum? And if you've said yes, the answer is correct. Not only do I have a global maximum at d, I also have a local maximum. How come? Because it still satisfies this definition. So if you look at d, if I pick an open interval near d, then that is the largest y value that this takes on in this open interval. So what we notice is in this picture, if I come back here, we could say we have or I could comment here in picture, and let me actually finish off this definition and we'll make some comments above it. So same thing happens for a local minimum. So if you look at this picture, where would my local minimum be? We'd have a local minimum at c. How come? Because if I pick an open interval, the y value at x equals c is smaller than all the other y values. So let's kind of define that. We could say f has a local minimum at c if f of c is less than or equal to f of x when x is near c. Okay, so the same thing is going on here. So if you look at this picture, what do we have? A local minimum at c. Okay, so we could say in picture above, what do we have? We have a local maximum at, where were they? X equals to b and x equals to d. Remember, at x equals d, not only do I have a local maximum, I also have a absolute maximum. And then what else do we have? We have a local minimum at x equals to c. Okay, now my question is, so once we're done with this, now my question is this. How about at e? What is this? Is that a local max or local min? In fact, the answer to this is at e, we don't have anything. How come? Because look, by definition of a local max or a local min, what do we need to prove? If I pick an open interval that includes e, I need to make sure that the y value at e is the smallest or the largest for it to satisfy local max or min. Here's the problem. See, if I pick an open interval that includes e, what happens? Is e the smallest y value or the largest y value? The answer to that is no, because what happens is if I go to the right of e, at this x value, what do you notice about my graph or my function? It's undefined. So this actually fails the definition of a local max or min, because no matter what interval I pick, how small this open interval is, when I move to the right of e, my graph is undefined. And if it's undefined, then I can't use the definition of a local max or min. So just to kind of summarize this, local maxes and mins will only occur when you have some kind of a hump or something goes down and it changes direction. So endpoints Okay, endpoints will never ever be local maxes or local mins because they fail the definition of a local max or a min. The only thing endpoints can be are absolute maxes or absolute mins, or they're nothing at all. So in E, notice how if this is either an absolute max or an absolute min, we'll define it. If not, then it's nothing. So this endpoint was an absolute minimum, but it's not a local minimum because, once again, it fails the definition of a local minimum. Because if I move to the left of A, this function is undefined. Okay, so keep that in mind. Local maxes and mins are usually at kind of like humps or things that change direction, goes from decreasing to increasing and so on. Absolute maxes and mins, if we have them at endpoints, it's okay, but we can never ever call endpoints local maxes or mins. Okay, so I hope this is clear to you. If you have any questions, any further questions about local maxes and mins, don't hesitate to ask me. Okay, so let's move on to our first theorem, which this theorem is called the extreme value theorem. Now, the extreme value theorem actually guarantees something for us, which is kind of nice. So here's what the extreme value theorem says. If f is continuous on a closed interval from A to B, then f attains an absolute maximum value and, or let's call it f of c, and an absolute minimum value, call it f of d, at some numbers c and d in the closed interval from A to B. Now, let's just pay close attention to the hypotheses, because remember, in each theorem, the hypothesis is very, very important. So what is this saying? This first statement is saying two things. Okay, f needs to be continuous on that interval, but more importantly, it needs to be continuous on the closed interval from A to B. So what this is saying, what the extreme value theorem is saying is, if your function is continuous on the closed interval from A to B, then you're guaranteed to have an absolute maximum and absolute minimum in that closed interval. So think of it this way. If I have, let me draw a couple of pictures. If I have something like this, from A to B, and I draw this picture, what do you notice? This is continuous on the closed interval, and this graph actually does have an absolute maximum and an absolute minimum. Where is my absolute maximum minimum? My absolute maximum is, and let's draw this a little lower just to make it clearer. So ignore this part. So what do I notice? My absolute maximum is at C, and my absolute minimum is at D. Okay, so notice how, as long as it continues on the closed interval, or I could have it this way, right? What if it looks like this? It's continuous on the closed interval from A to B, but what do you notice? My absolute minimum maximum are at the endpoints. And remember, endpoints can be absolute maxes and mins. And in this definition, what did we call the absolute minimum was D, so that's D. And my absolute max was C. So actually the endpoints ended up being the absolute maxes and absolute mins. Okay, so what does the extreme value theorem guarantee? It guarantees that we should get an absolute maximum and absolute minimum on an interval as long as the function is continuous on the closed interval. So let's just kind of make a comment here and show you why the hypothesis is important. So it is important that both hypotheses are true. And I'm saying both hypotheses, there's really just one, but I'm kind of treating it as two. So what's the first one? It has to be continuous. Okay, so what I'm saying is, like, what if I give you something like this? See, this graph from A to B, it's not continuous, right? So what's the problem here? This actually does have an absolute minimum, but it doesn't have an absolute maximum. How come? Because you can never ever get to this open point. You can just get infinitely close. So we could always play that game, like if you pick a number, I could pick one larger, and you could pick one larger, and you could pick one larger. So this actually does not literally have a maximum. So what we know that this has a min, but no max. And we should maybe be more specific, an absolute min, an absolute max. Okay, so this has a minimum, but not an absolute max. Now, what if it's continuous on the open interval, but not on the closed? So what if it does this? This is A to B, from A to B. Notice how this is definitely continuous on the open interval, but it's not continuous on the closed. And what do you notice here? So this is not continuous on closed interval. Which, what do you notice here? This has actually, does it have a maximum? No, because it goes on forever. And it doesn't have a minimum either, because you'll never ever get to this y value. You just get closer and closer. So this has no absolute max or minimum. So you could see that we care about continuity, but more importantly, it has to be continuous on the closed interval. Okay, so that's what the extreme value theorem is all about. Now, moving on to our next theorem, which is actually, it has a name as well, which is called Fermat's theorem. Okay, so here's what Fermat's theorem says. So here's the hypothesis for Fermat's theorem. So if f has a local maximum or minimum at C, and if f prime of C exists, then f prime of C should equal to, and so let's leave it blank and kind of talk about this. You guys should be able to figure this out. Let's draw a picture here. Think of it this way. If I tell you that you have a local maximum or a minimum, we all know what local maxes or mins look like because we just talked about them earlier. Remember, it kind of has to have this hump, or it's, which is C, or it could look like if it's a minimum, it has to have a hump. So we're saying it doesn't matter if it's a local max or a min at C. What could you say? Think about it. F prime of C. What would f prime of C be in these pictures? So if you look at it, by definition, what do we know? What is the f prime of C described? Isn't this the slope of the tangent line at x equals C to the curve? So if I were to draw the slope of my tangent line here and here, what do you notice? What must f prime of C be? If my tangent lines are horizontal, then f prime of C must be 0. So what does Fermat's theorem guarantee? It says, look, if you tell me that this function has a local maximum or a minimum at C, then I know that the derivative at C should be 0 as long as it exists. Okay, so basically, we get our derivatives for free. Now, here's my question for you. Is the converse true? So take a minute and think about it. What's the converse? Basically, what I'm telling you is if f prime of C equals to 0, or if the derivative at C is 0 or it doesn't exist, does that mean f has a local maximum or minimum? Okay, so be careful about this. So think about it. If you want, pause it, think about it a little bit, and then press play again. But if you've answered no, you're correct. So be careful with Fermat's theorem. What Fermat's theorem says is, look, if you have a local max or a minimum, and if your derivative exists, then we know that the derivative at that x value must be 0. But the converse is false. So we can't say just because my derivative is 0, I'm guaranteed to have a local max or min. Okay, so the answer to this is no. Okay, so here's what we could say, and here's my counterexample to this. Take f of x equals to x cubed at x equals to 0. What do you notice here? Notice f prime of 0 is 0, right? Because if you find the derivative of x cubed, it's 3x squared. When you plug in 0, you get 0. So notice how my derivative of x cubed at 0 is 0, but f of x, if you know what the graph of f of x looks like, which we all should, this does not have a max or a min at x equals to 0. Okay, so what we could say here is, in fact, if you look at this graph, that's what it looks like. So clearly this graph at 0 does not have a max or a minimum. Okay, so it's very important to understand from Mott's theorem that if we have a local max or min, and if the derivative exists, then we're guaranteed to have our derivative equal to 0 at that value. Now, how do I think of this? See, what I would say is, if my derivative is 0 at a specific value, that could be a potential local max or min. So in the future in this class, we're going to look for local maxes and mins, and our interest is going to be where the derivative is 0. So remember, just because the derivative equals to 0 at a specific value, it doesn't guarantee that we have a local max or a min, but it's a potential local max or a min. So it could be a local max or a min. So there's going to be ways that we're going to check to see, hey, is this really a local max or a min, or is it not? Okay, so we're still interested in where the derivative is 0, but just because it is 0, we're not guaranteed to have a local max or a min there, but it could potentially be a local max or a local min. Okay, so just keep that in mind. Okay, so let's move on. Now let's define our next term, which is a critical number. So what we could say is that a critical number of a function f is a number c in the domain of f such that either f prime of c equals to 0 or f prime of c does not exist. Okay, so this is actually important. So when we talk about critical numbers, what does that mean? Critical numbers make my derivative either 0 or undefined. Okay, now here's the one important thing I want to point out to you. The critical numbers that you find, okay, for a function, you need to make sure that those critical numbers are actually in the domain of f. So what I'm saying is, sometimes you might give false critical numbers. So in other words, think of it this way. If I have f of x equals to the square root of x, okay, what do I notice here? If I find a derivative of this, what is the derivative of this? It'll be 1 over 2 rad x. Now, my question to you is, the derivative of f, which is 1 over 2 rad x, when is this 0? When you look at this, actually the derivative never equals to 0. Okay, so then the question is, when is this undefined? Well, you notice that this is undefined in infinitely many places. Does that mean I have infinitely many critical numbers? And the answer to that should be no, because look, where is this guy undefined? At 0. So if you look at this, then you say, okay, this guy's undefined at x equals 0. Now, my question is x equals 0 in the domain of f? In fact, if you look at the domain of f, what is the domain of f? It's 0 to infinity. So it includes 0 and goes to infinity. So in fact, 0 is a critical number because it's in the domain of f. Now, you would also notice that this guy's also undefined at -1. But why is -1 not a critical number? Because it's not in the domain of my original function to begin with. So if you notice here, what we notice here is that the only critical number is at x equals 0. So the only critical number of f of x is at x equals 0, because at x equals 0, my derivative is undefined. Remember, critical numbers only occur when your derivative is 0 or undefined. So in this case, the only place that my derivative was undefined, which is 0, that was in my domain of the function to begin with. Okay, so moving on, we have a couple more theorems, and then this will pretty much wrap up this section. Okay, so theorem. If f has a local maximum or minimum at C, then what could we say? See, from Mots theorem, we said, look, if f has a local maximum or minimum at C, see, from Mots theorem then said, if f prime of C exists, then f prime of C must be 0. Now, what are we saying? If we have a local maximum or minimum at C, then what could you say? Whether f prime exists or not, what could we say here? We can then say for a fact that at x equals C, we have a critical number, because what do we know? At local maxes or mins, my derivative is either going to be 0 or it's not going to exist. Okay, so what do I mean by that? A local max or a min. See, what do I have here? I have a local max here, except my derivative does not exist here. Now, if I draw this, I have a local minimum here, except my derivative is 0. So in either case, when my derivative does not exist or if it's 0, those are what critical numbers are. So what we could say is that then C is a critical number of f. So if you look at this theorem is a little similar, to Fermat's theorem, but it's not as specific. See, what's the difference? Fermat's theorem says if the derivative at C exists, then we're guaranteed that f prime of C is 0. This one just says, look, if I have a local max or minimum at C, then I know C is a critical number, okay? Which is kind of being more general as far as what it is. Because if this is a critical number, then we know that my derivative is either 0 or undefined. Where Fermat's theorem only specifically focuses on where my derivative is equal to 0, okay? So the last thing I want to talk about is called the closed interval method. So the closed interval method basically is a method that allows us to find absolute maxes and mins of any function on a closed interval. So remember, obviously, you have to be given a closed interval. So here's what we want to do. To find the absolute maximum and minimum values of a continuous function f on a closed interval from A to B, we're going to do three things. Now, one thing I want to underline here, remember, the closed interval method is used to help us find the absolute maximum and minimum. Okay, so This isn't going to help us find local maxes and mins, because we're going to come up with other ways of finding local maxes and mins. So remember, this closed interval method is only going to be used for functions where you're trying to find its absolute maximum or minimum on some closed interval, okay? And of course, we know that the function has to be continuous on that closed interval, and here's how we're going to find it, okay? So the 3 steps we follow. The first thing we do is we find the values of f at the critical numbers of f in the open interval from a to b. Okay, so what are we doing here? To find the critical numbers of f, we just find the derivative of f, and we find out when the derivative is 0 or undefined in this open interval. And then what do? When you find those critical numbers, you plug them into f. So what we're basically doing is this. If I have a function that kind of does this, what am I doing? I'm finding this critical number and this critical number. And then once I find those critical numbers, I plug them into the function to find the y values. Okay, so I'm finding this y value and that y value. Because what do you notice? If I have an absolute max or an absolute min, it could be at my critical numbers, can't it? So that's step 1. Step 2 is, if you remember earlier, what else did we talk about? My absolute maxes and mins could also be where? It could also be at the endpoints. So it could be here and here. So then what you're going to do is, finding the y values at the endpoints are easy because the endpoints are a and b. So the second thing you're going to do is you're going to find the values of f at the endpoints of the interval. So then what you're doing is you're finding the y values at the endpoints, okay? And then once you do that, then we're pretty much done. Because from these 2 steps, what do you notice? The largest value from these 2 steps is your absolute max, and the smallest value from these 2 steps is your absolute minimum. So other than these 2 steps, there's no other place where you could have an absolute max or an absolute min. So this closed interval method, these first 2 steps guarantee, or basically guarantee, that we could find my absolute max and min through these guys. So the third step would be the largest of the values from 1 and 2 is the absolute maximum. And the smallest value is the absolute minimum. Okay, so that basically wraps up this section. Now, I know we didn't do any examples, but I feel like this section had just a lot of definitions and theorems, and I figure that you guys could probably find critical numbers. Once you know what a critical number is, that just means find a derivative, set it equal to 0, and find where it's or find where it's undefined or where it equals to 0. And same thing with the closed interval method. So when you work on the problems in class, obviously you're going to put these to use. So the main kind of purpose or focus of today's section was just to define a bunch of these things. Now, of course, we'll further our knowledge on finding local maxes and mins and different things later on in this chapter, but today was strictly just defining a bunch of things, and of course talking about important theorems like Mots Theorem and so on. But remember, if you have any questions, feel free to ask me and I'll be more than happy to answer them. So now you're pretty much ready to work on some problems from section 1.